Hi, my name is Rowell. I'm here to share a message of hope and how a project in Indonesia has helped transform it from a mere possibility to tangible reality. I will be introducing solar power in biological form, applied in a way that fixes carbon and makes water at a massive scale. There are two parts to this story, and we'll start from the processing of organics and later on touch on how to sequestrate carbon into soils. In aerobic composting, the idea is to add oxygen into organic waste materials such as food waste, green waste, manures, really any organic material. You can blow the oxygen in, you can turn it in, there's a whole variety of ways. But what this does is it oxidizes 70% of that material into atmosphere and release GHGs, including carbon and nitrogen oxides, water vapor, and you finish with 30% of that nutrient left over, which we call compost. So this is spending energy to burn off nutrient, losing most of it as GHGs into atmosphere, which now cannot meaningfully contribute to soil or agriculture. And therefore, degrading organic material this way drives emissions. At the same time, the definition of biogenic CO2 refers to carbon in organic waste material that was originally removed from atmosphere by photosynthesis and under natural conditions cycles back to the atmosphere as CO2. Now, what if I told you that there's a way to process that same organic material, whatever it might be, that does not spend energy and does not produce an emission? Follow me on this journey. We must start here, and it starts with photosynthesis. Let's start from the type of photosynthesis that is familiar to everyone, where green plants capture the energy of sunlight and then store that energy in carbohydrate molecules. Here, only a portion of the visible spectrum is absorbed. This is a really small slice of the total EM spectrum that is freely available from the sun. Well, how about the rest? Nature works well beyond what our eyes can visibly see. And as it turns out, billions of years ago, before photosynthesis evolved in plants, microorganisms were already actively using the rest of the EM spectrum, and they still do today. And the way they work completely changed the way we think about the carbon and water cycle. An entirely new field of biosciences was developed, where this energy collection happens in 3 dimensions, underwater or underground, 24 hours a day, manufacturing water as a byproduct, and sequestrating gaseous carbon. In short, a nature-based solution for fixing carbon and making water. So VRM developed a bunch of methods aimed at growing that reaction using organic waste material to allow for low-cost, decentralized mass production anywhere in the world. And this is a simplified cutaway diagram that leverages on biological solar power that ultimately results in the accumulation of living humus without producing net emissions. The process is simple, typically costs less than landfill, and has a 100% conversion rate by mass without pest, pathogen, or odor problems. The process, which does not require external energy to be spent in putting GHGs into the atmosphere, resulting in a 100% conversion and productization rate. The emissions from conventional practices is completely avoided. And this is because regenerative upcycling of organic material recaptures avoidable emissions. The takeaway here is that there's a world of difference between these two. And if we relook at this statement, right, there is a type of photosynthesis that cycles not into atmosphere, but into the soil, not in the form of CO2, but as soil organic carbon, living humus, and not a degradation process, but due to regenerative processes. Now here's a crash course on how to run the process. Don't worry, we have a few countries helping us out here, and Malaysia will start. So we collect organic material, we calculate the dosage needed, we dilute and we spray the photosynthetic catalysts on, then we pile it up like how Thailand is doing it here, or in land-scarce Singapore where they pile it 18 meters high. Then we make sure there's a dip in the center of the pile and cover it up, just like how the Philippines has just demonstrated it, and you're done. You can do the same process in the desert like how the UAE is doing here in Ras Al Khaimah, and exactly the same thing on the other side of the planet in Australia. We could use mechanized methodologies for large-scale applications, just like how the United States is demonstrating right here, or as creatively as how China is doing it in an old landfill site deliberately recapturing methane into the process. But it is the project in Indonesia that really combines the various best practices to maximize the positive social and environmental outcomes by adapting the technology to their unique circumstances. And by the end of the year, we would have the same process open in Saudi Arabia and in Jordan and in Egypt. And regardless of where it is made anywhere on the globe, we end up with a carbon-rich, a humified organic carbon, which is literally chock full of life. The material is moist, fresh, it's a living material that has an earthy petrichor scent that is best described as the smell you get before the rain in a forest, and has diverse fungal populations. It is dense, it's heavy with moisture that is locked within the humic acid that is constantly regenerated within the material. This is the fundamental building blocks of carbon-based life in the soil, and for that reason, we call it humisoil. We've got a few samples flown in from Southeast Asia, and I encourage you to take the time to experience it yourself at the Indonesian pavilion. And this is where part 2 starts. When we add this material into depleted soils, we're allowing for the stabilized photosynthetic reaction in the humisoil to turn the entire treated area into a giant biological solar cell. The land continues to fix carbon, make water, trigger topsoil formation, gradually regenerating the soil ecosystem biodiversity. It acts as a secondary underground photosynthesis, which supports plant-based photosynthesis. The resultant impact on food production from terraforming depleted land into arable soils can be quite visual. So this picture was taken from a farm where the change occurred in about 7 months from left to right. And accompanying the change in the soil, that's the response of the plants from left to right. And in Thailand, a chili plantation went from this to this. And Australia, pharmaceuticals, left to right. And in the Philippines, growing rice from left to right. And a golf course in Singapore, sand to soil. And in China, rice grown in saline alkali soil before and after. And in Indonesia, pineapples from left to right. And here in the UAE, fodder for grazing animals before and after, just like how they do it in Malaysia, exactly the same. Depleted soils from left to right. Regenerating the soil and moisture, it drives economic outcomes, which in turn improves food security. So it's decarbonization that is driven by soil regeneration. And as the soil carbon accumulates over time, given enough time, carbon can accumulate vertically, just like in this picture. Here's a tree that's 20 years old, so you can see that original soil horizon. And on the right side of this picture, that's sugarcane, where somehow that topsoil layer is now more than 400 millimeters higher than the surrounding soil horizon. How do we account for 4,000 cubic meters of material extra per hectare? How do we do that? We've tried to quantify it. For example, here's a hyperspectral satellite picture of an area that was going through 4 years of drought in Australia. More green in this picture means more photosynthesis, and more red means soils that are barren. And turns out that treated soils over a longer period of time are pretty much completely green. So this tangibly shows the impact of that accumulating carbon. Now we can imagine a future where the farmer gains a potential new income stream. Number one, he produces food, but now, number two, his underlying soil can act as a permanent and massive carbon accumulating sink at the same time. The soil, not the crop. So case studies worldwide today are suggesting about 20 tons carbon dioxide equivalent unit sequestration potential per hectare and per year. We are working on methods to quantify this, and we're in the process of submitting a new carbon methodology to account for this. Quick recap. We upcycle organic wastes through an emissions-free catalyst production method to continue that soil photosynthetic reaction and catalyze the biological carbon sequestration and water manufacture in improving soils and therefore achieve better food security, hence leveraging organic wastes for regenerative climate solutions. All of what you've just heard has been published as a best practice in the textbook, An Introduction to Circular Economy, certified as a soil carbon amendment by the USDA, recently presented at the UN and the FAO level, awarded by the CCAC, projects in 33 countries and territories, supporting 12 out of 17 UN SDGs. So quickly, we're going to share an ongoing project with Saudi Arabia for a sense of the sort of impact in the GCC region. Here, we're combining elements of the circular carbon economy framework together with the Saudi Green Initiative, which is meant to terraform 40 million hectares of soil through the accumulation of carbon into the soil carbon pool, and hence reducing irrigation needs by 50% or more. So, for less than the cost of the water savings for the project, when applied to say half of the SGI or 20 million hectares, the data thus far is pointing towards a carbon sequestration potential of 136.5% of the entire carbon emissions of Saudi Arabia at 0.8 gigatons per year, decarbonizing atmosphere through the recarbonizing of soils towards an arable Arabia, one where carbon is not the enemy and carbon is a friend. And this short presentation here hopefully provides sufficient technical context to better understand Indonesia and Jarum Foundation's work, considered to be a global best-in-class for 2023. Their decisive leadership and innovative spirit in adapting this technological tool to maximize local impact has resulted in truly amazing outcomes which has inspired many others in the ASEAN region and beyond. Do save this QR code where we openly share information, including a download of this presentation. So take a picture here and save it for later use. My name is Rowell, Chief Sustainability Officer of VRM Biologik, and on behalf of the team, the Indonesian government, and our gracious hosts, the UAE, I thank you for this opportunity to share.